Hey guys, today we're going to be covering acids and bases. And your assignment today is already posted online. It's only a one-page assignment and it has to do with naming acids and bases, which we're going to get into. So there are many compounds that you're familiar with that are acids or bases. So lemon juice, soap, oranges, pop, vinegar, baking soda, all these things are acids or bases, whether you realized it or not. Acids and bases both can be very dangerous. We generally think of acids as very dangerous, but bases can be just as dangerous. Because they can both be very corrosive. So never try and identify an acid or base by taste or touch. You're always going to be doing a test to determine what the acid or base is. So acids and bases is measured, the strength of acids and bases is measured on a pH scale. And it's little p, capital H scale. So to have a pH of below 7 means it's acidic. If the pH is above 7, it's basic. And if the pH is equal to 7, it's neutral. So if we numbered those out, all these blue ones are base or bases. All the red ones are acids. And our lonely little 7 is our neutral. So acids are special because they release hydrogen into solution. So when you dissolve them in water or you put them in a liquid, they're going to give off hydrogens. And usually if you see square brackets like this around an element or an ion, that means concentration. So it means how much of it is being released. So it releases hydrogen. So if say we have HCl, which is a gas, and we put it into solution, what's going to happen is this is actually going to split up into hydrogen in its aqueous form because we put it into solution, and chlorine, again aqueous because we put it in solution. But this hydrogen is released in the form of a hydrogen ion. Bases, on the other hand, these guys release hydroxide. Whoop. Look at me using the wrong brackets. They release hydroxide, or an OH group, into solution. So if you have NaOH, sodium hydroxide, which is a very common base, and you put it into solution, you're going to have sodium in solution, and you're going to have hydroxide in solution, because this hydroxide group gets released as a hydroxide into solution. So this produces hydroxides, whereas the hydrogen or the acid produces hydrogen ions. This is really important because if you think about it, if the acid is releasing hydrogen and the base is releasing hydroxide, when we put those together, what do you think we make? Remember, if we, with our acid-base kit in our classroom, if we spill an acid, we add a base to neutralize it. And if we spill a base, we add an acid to neutralize it. So if we take an acid and add a base, this actually gives us water. We have our 2 hydrogens and our 1 oxygen, which makes it neutral. Oop. Don't want that picture yet. Almost though. So pH is the concentration of hydrogen ions, but as a logarithm, which means every time this goes up by 1, it's actually a change of 10 times the concentration. So if we have our numbers again, so if we go from 4 to 3, this is 10 times more acidic. Which means if we go from 4 to 2, this is 100 times more acidic. But the opposite is true for base. If we go from 10 to 11, this is 10 times more basic. And if we go from 10 to 12, this is 100 times more basic. So, I really liked this picture and I wanted to make sure that you guys could see it. This shows you all the way from pH of 0 all the way up to a pH of 14, and it shows you some common examples that you may know. Some you may not realize what the pHs are. So lemon juice is a pH of 2. That's really strong. That's approximately the same as your stomach acid. Wine is a pH of 4. Rain is a pH of 5.5. That makes rain acidic, doesn't it? Because it's less than 7. And we are going to be talking later about acid rain. Human blood is 7.5, so we're a bit more basic than neutral, but we're pretty neutral. Baking soda is 8.5, so not a very basic base. Detergent's a 10, so that's quite basic. And bleach is surprising. Bleach is 12.5. That's all the way up here. That is very basic. The more acidic and the more basic something is, the more corrosive it tends to be. Okay, so acids, if we're just looking from 7 to 0 or 0 to 7, depending on how you think of it, these guys, stomach acid, it's around a 1, it's close, I do believe, to a 1.7. Lemon juice is a 2. Vinegar or cola is a 3. Tomatoes are a 4, so that's rather acidic. That's why people complain about acid reflux or heartburn when they eat tomatoes, because this acidity added to your stomach acid makes it too acidic. Black coffee is about a 5. Distilled water and human urine are about 6, and human saliva is about 7. So all of these acids, they have a pH of 0 to 6.9. They give off hydrogen ions. They conduct electricity because of these ions. Remember, anything with an ion tends to conduct electricity. They produce hydrogen gas, which again isn't very surprising when it releases hydrogen ions. And these guys are corrosive. So, acids, you can generally tell when something's an acid because it usually starts with hydrogen. There are some exceptions though. So a common one you'll see is HCl. And this is hydrochloric acid. HNO3. This is nitric acid. The big exception is acids that start with a carbon, or acids with a carbon. Will actually have the carbon come first. So the big one with this one is going to be our CH3COOH. And if you remember, CH3COO, that is acetate. And this one's called acetic acid. And don't worry, we're going to get into the naming a little bit later. So hydrochloric acid, this is a really common one that you guys will see. This is found in a lot of cleaners. This is just something that you often see in your household. So let's get into naming though. There are 3 rules for naming. If it's a hydrogen, plus something that ends in "ide," you are actually going to call it hydro, and then you're going to follow it with the name, but end it in "ic" instead of "ide" acid. So a good example of this is our HCl. This is hydrogen chloride, so we have hydrochloric acid. You can also do this with HF. We have hydrogen fluoride, so this is going to be hydrofluoric acid. Beware with fluoride. I noticed you guys on your naming sheets, you were spelling it F-L-O-U. It's not fluoric or fluorine, sorry. It's fluorine, so it's U-O. Another naming is when you have hydrogen and then something that ends in "ate." So this would be like the acetate, or this could be phosphate, carbonate. And what you're going to do is you're going to just have the name, but change the ending to "ic" and acid. So remember, acetate and hydrogen makes acetic acid. Another example is H2CO3, that's hydrogen carbonate, and that will be carbonic acid, because you're changing that carbonate to carbonic. The last one is going to be hydrogen, and then something that ends in "ite." So again, phosphite, sulfite, these are common ones, and they're going to have the word, but the ending is going to be "us," and then you put acid. So if we have H2SO3, this is hydrogen sulfite. So this one's actually called sulfurous acid. So with sulfate, sulfite, and sulfur, we generally add this UR because sulfus just doesn't sound very good. It doesn't really work. So we'll add the UR, so it's sulfurous acid. Okay. So bases, on the other hand, are much simpler when it comes to their naming. But let's look at their characteristics. So bases are anything from pH of 7 all the way up to 14. So between 7 and 8 we have human blood and seawater. Baking soda, again, is around the 9. I think 8.5, 9. Milk of magnesia, it's 10. Household ammonia is 11. So that's getting quite high. Oven cleaner, 13. And drain opener is 14. So that can be very corrosive depending on its concentration. So these guys donate hydroxide groups into the solution. This can be neutralized by adding a hydrogen ion. And when you do that, like I said, you get water. If you take hydrogen and you add a hydroxide group, you get water. And it becomes neutral. These guys, again, conduct electricity. Remember, the key for that is if there's ions, it will conduct electricity. These are slippery and are caustic. So every year I have someone who's super excited that they get to play with a base, and they get it on their fingers, and they always come running, giggling, "Mrs. Cote, look, it's so slippery." Not realizing that it was actually eating away their fingerprints, and that's why it was so slippery. It's not a permanent damage. It comes back, but they're literally taking layers of skin off, which is not good. So if you know the compound's chemical formula, you'll be able to identify it as a base because it usually ends in an OH group. And the naming is just basic naming with hydroxide. So common ones are NaOH, which is sodium hydroxide. We also have MgOH2, which is magnesium hydroxide. CaOH2, calcium hydroxide. So as you see, all we're doing is naming the metal and then putting hydroxide at the end. Even NH4OH, it's ammonium hydroxide. So the naming conventions for this one, there's nothing special to remember. You just have to name it just as we were doing before. So why is it important to maintain pH? Well, to maintain pH, most living things require a pH of between 6 and 8. So most living things, there are things that prefer an acid, there are things that prefer a base, but most things require a pH between 6 and 8. So nothing too acidic, nothing too basic. But there are times where the pH is very important to the environment, whether destructive or beneficial. And two main ways are acid rain and agriculture. And as you can see through this picture, the first picture was taken in 1908, and the second picture was taken in 1968. Both of these are of the same statue, and you can kind of see how it is the same statue, but the acid rain has caused reactions on the stone and caused the features to be ruined and all the detail work to be ruined. So if this was taken in 1968, it would be really interesting to see what that statue looked like today, even if it was even around. In agriculture, if you plant hydrangea, oh, I can't talk and you guys know that. If you plant it in acidic oil, you get this pink flower, whereas if you plant it in basic soil, you get this purplish blue color, which is kind of cool, but it shows that the acidity or the pH is actually very important when it even comes to plants. So to be able to determine the pH of something, we have something called pH indicators. And if you guys ever had a pool or knew someone with a pool or a hot tub or worked at a pool, this is something that you actually have to check on a regular basis. This one is a little slip of paper, usually called litmus paper. There are different chemicals that you can use instead, called indicators. This one's really cool because it goes from a pH of 1 all the way up to 10, which is quite a broad range. And as you can see, each pH level is a different color. So if you look at this top one, it's a really dark blue, which means they must have dipped it in something basic because it has a pH of about 10, if not higher. This bottom one is a very bright orange. So if we compared it, and with a picture it's harder to do, but what you'd actually do is you'd hold it above each of these and see which one it matched the best with. It looks to me to be about a pH 3. But this is one way to figure out the pH. If you go into Chemistry 11 and Chemistry 12, in Chemistry 12 you do something called titrations, where you're actually figuring out the pH of different things. Another way to do it that you can actually do at home is using red cabbage, and this gives you a range of 1 to 12 depending on what you put it in. I did contemplate getting you guys to do this, but it requires some special ingredients and some special stuff that I didn't want you guys to have to leave your house and go get. But yeah, from a pH of 1, it's this reddish color, all the way to a pH of 12, it's this yellow, which I found really interesting, that using things like rubbing alcohol and red cabbage, you can get basically a testing kit that would work on a range of pHs. Okay, so in water, and this is the last thing we have to do. So in water, the concentration of hydrogen is equal to the concentration of hydroxide. Which is why it's neutral. So by definition, pure water, H2O, is neutral. Because the concentration of hydrogen is equal to the concentration of hydroxide. If a solution is acidic, the concentration of hydrogen is going to be greater than the concentration of hydroxide. Whereas if a solution is basic, the concentration of hydrogen is going to be less than the concentration of hydroxide. Okay, so like I said, your assignment today is going to be the acids and bases worksheet. I have included the answer key so that you can check your answers. Remember, for the acids, you will need to remember your 3 different rules. If it's ide, ate, or ite, how you change the naming. With the bases, remember, don't make it complicated. It's just basic naming with hydroxides. I am going to be giving you a quiz on this probably next week. It's going to be online through a Google form that you will fill in. You will be getting a mark update later this week with a pseudonym, so a fake name for you to put into the document. I hope you guys are all safe and well, and I'll talk to you later this week.